Hi everyone. Everything from my end looks good, but if you can in the chat, just tell me if you can hear me and I'll start. Remember, there's a 30-second delay, so I will see if there's a problem in 30 seconds. So you might see me, you might see the problem persist for a bit before I address it. But sounds good. Okay, yeah. Okay, good. Yeah. Um, I never totally trust this interface. It says that everything is good, but I don't know. Okay, so let me begin. Now, I think you guys have already noticed that each of my videos, my lecture videos, are on one topic. Okay, and some of them are short, some of them are longer, and there's no way for me to actually have them fit into the hour and a half, or I guess hour and 20 minutes that we would have had in the classroom. And so this week I actually had you watch 2 hours of video. So I'm gonna limit this live stream to 1 hour. I'm sensitive to the to your time commitments, and I apologize for this, but I had to make a decision, and there was just no way to chop these things up that way. So if it's inconvenient for you, I apologize, and I'll try to accommodate you the best I can. But this might happen, and it might happen again. Okay. Nonetheless, your total contact hours with me are going to be at least 3 hours. And of course, if you want more, I'm more than happy to do more. I'm just sticking to the 3 hours per week because that's really what the expectations are. But if you need more, I mean, there's the Google Hangouts in the evening. If you guys want not all of you, but if some of you want an extra live stream, I'm happy to do that too. So I'm not trying to decrease the amount of time we have together. I'll only increase it, but I won't expect you to do more than 3 hours a week. So that's the way we'll proceed forward. I only have two questions really for you today. The course is just winding up, and what you should have watched leading up to this live stream are the two videos that I gave you earlier in the week, and one of them was on 1D kinematics, but under the assumption of constant acceleration, and the other one was on simple harmonic motion. Okay, so we're just going to do one problem for each of those. The simple harmonic motion is actually easier than the 1D kinematics constant acceleration. Okay, and so 1D kinematics in general is pretty hard because it requires calculus and stuff that I didn't even teach you about. Okay, and we went over that last week. But what you can do is you can take general kinematics and you can apply it to specific situations that are very typical. Okay, and the two very typical situations that we study are going to be falling, because things fall and on the surface of the earth, and the other one is oscillation, which you could just think of anything vibrating. Like, you can imagine any kind of a fiber, it'll just vibrate back and forth if you flick on it, like the little fibers in your ear that allow you to hear. That's how you're hearing me right now. But anything like, like a pane of glass, if you knock it, or a pendulum, that swings back and forth. And so all of that is covered under the kinematics that we're going to do. Okay, so having said that, here's our first problem. The first problem is a rock, and we're going to drop it from the top of a skyscraper. And I didn't say that here, but I should say just drop it from rest. In other words, we're just going to let go of it like that. Okay, don't worry on tests and stuff like that. I'll be very clear with the language, but since we're doing this together, I can be a little bit more relaxed. So we're going to drop a rock from the top of a skyscraper, and as it falls, we're going to watch it, and it's going to fall past two windows. When it falls past the first window, it's found to be traveling at 10 meters per second. So I say a rock is dropped from the top of a skyscraper. It is found to be falling at 10 meters per second when it passes the first window, and 50 meters per second when it passes the second window. Okay, that's all I give you. All right, I'm going to ask you two questions. First question is, how far apart are the two windows? Okay, and the other one is, how long does it take the rock to travel from one window to the next? Okay, so there's our question, and let me just take a quick look at the chat here. And all right, doesn't seem like anyone asked anything further. Okay, so how do you do this? Well, you saw questions like this in the pre-recorded lectures, but there you kind of had these polished solutions. So let me show you. I'm going to switch to my whiteboard. Let me show you how you would set this up, okay, how you would proceed. The first thing you want to do is you want to draw a diagram, okay? And there's two steps to drawing this diagram. The first step is just kind of draw a picture of what's going on. So you got a skyscraper, you got a rock that's falling, and it's passing by two windows, okay? So let me switch to this whiteboard here, okay? And it's kind of hard to draw with it, but I think I can do it, all right? And so the first thing you do is you maybe just draw a skyscraper like this, okay? And here's your first window, and here's your second window like that. And of course the rock is falling, so it's kind of hard to draw like a movie here, like, you know, things, but here it is. Here's the rock going down like that, okay? And it'll pass by the first window here, and there's our second window there like that, okay? And that's it. That's the first thing you ought to do, all right? So just draw that. Now, the second thing you ought to do, so draw a picture of the verbal description of what I gave you. Okay. Sometimes on a problem, I'll give you a picture. Sometimes you can just get it out of the verbal description. The second thing you need to do is you need to add a ruler, a coordinate system as it's called. Okay, but just think of it as a ruler. And the ruler has got to go like a ruler is a straight edge, and the ruler's got to go straight along the motion here, because this is 1D motion, all right? It'll be different when we get to 2D, but this is 1D motion. So right now the motion is down, so you want a ruler that goes either up or down, okay? Now you can orient the ruler any way you like, but in my opinion, the best way to put the ruler is so that up is positive, okay? And I'm going to do that from now on, and I recommend you do that as well, okay? So next thing, so step number 2 is, and I'll do it in a different color here because I can, is I'm going to put a ruler here, and that's the base of my ruler, and here's my ruler going up like that, okay? I know it doesn't look like a ruler, but just imagine that it's a ruler. And over here I'm going to put a little positive there because that indicates the direction of positive, okay? So there's step number 2. Just if you have any questions, just type them into the chat. 30-second delay, so I'll go on, but I'll look back and make sure that I catch whatever you've said, okay? So there's the second part, okay? Now whenever you put a ruler onto something, because you're going to measure it, you're going to measure, say, a length, you get to put the 0 wherever you like. That is, you get to put the 0 of the ruler wherever you like, okay? You could put the 0 here at the second window, you could put the 0 at the first window, you could put the 0 at the ground level, or you could put the 0 at the top like that. Now, some of these choices are better than other choices. If you put it at the bottom, then you're kind of stuck because you really don't know how high window number 2 is, and you don't know how high window number 1 is. All you want to, and actually you want to calculate the distance between the two. And so you get to choose, and you may wonder, geez, where should I choose my 0? It's up to you. And I'm going to choose it right here at window number 2, okay? So looking at the chat very quickly there. All right, and yeah, dog reveal later, Zach. Yeah, maybe next time, okay? And I'm just not ready for it. Okay, so over here, that's where I'm going to put a little line like that, and that's my origin. That's going to be x equals 0, like that, okay? Great. Now, that's the diagram, all right? Now, the next thing is you can start to put on this diagram what you know, what your known quantities are. Before I do that, let me switch back to the this screen right here. And so we're answering actually number A first, how far apart are the two windows. I've got this ready, so I'm going to cut and paste. This may seem like I'm typing very fast, but I'm just going to cut and paste here and put in here, whoops, the 3 equations, okay? So what you should see here are 3 equations. These are the 3 equations that I gave you in that lecture, okay? The first equation expresses the position as a function of time. The second one expresses the velocity as a function of time, and the third one expresses the velocity as a function of initial velocity, acceleration, and distances, okay? Now, we need to understand what these symbols are, and I think this is one place where students make their most mistakes. It's they don't know what each of the symbols mean, okay? So let's look at the ones with the little O's on them, the x naught and the v naught. X naught is your initial position. This is your position at t equals 0. Okay, v naught is your velocity at t equals 0. And you can see there's an x naught there and a v naught there. there's a V naught there, there's an X naught there, like that, okay? And those are initials, okay? And so when we go back to that diagram in a second, I'm going to ask the question, do we know this initial value? Do we know the initial position? Do we know the final position? And so on, okay? And we'll see if we can write in some of those numbers. All right. The second thing is there's also the final values. So there's the values after some time t. And so x is different than x naught because x naught is the initial position, x is the final position. Okay. And v naught is the initial velocity, and v is the final velocity. V naught is the initial velocity, v is the final velocity, like that. Okay. And a here, oh, t is the time. Okay. The time it takes to go from the initial to the final situation. And a is the acceleration. And because we're falling, the acceleration due to gravity is, let me type it in here, the acceleration due to gravity is actually 9.8 meters per second squared. But in this course, we're going to round it off to 10. Okay, why? Well, it is a bit of an error. In the lab, we really shouldn't do that because you can measure it pretty accurately. But I'm going to do that because it just makes the math so much easier. The arithmetic just so much easier. So it's not that big a deal. We'll do that on the tests too. Some professors do it. Some professors go, no, let's stick with the 9.8, and but we'll just do the 10. Okay. All right. Now I'm gonna have to put a negative sign in there in a minute, but let's go back to the diagram and we'll see, how we make use of this, like what we should do here before we start to plug into these three equations. If you just try to plug into them right now, you're probably going to make a mess. You're probably going to mess things up. Okay, so that's why this diagram is critical. Quick look at the chat. How did you figure on the A value? Oh, yeah, so the A value, the value of the acceleration, because we're falling, okay, it's falling on Earth. I didn't say it was on the moon. So if I don't say it's on the moon or whatever, if I say I'm falling on Earth, then that is a known value. The acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared. Now, should you memorize that? I don't know. I mean, it's a pretty easy number. There's not a lot of numbers to memorize. But on the test, I'll probably just give it to you. I'll give you a bunch of constants, and we will use 10. That's really easy to remember, I think. Okay. So if that doesn't answer your question, well, then, just ask again, Anthony. But I think, that's where I got it. Okay. It's simply a value, which is because you're falling on the surface of the Earth. Falling due to gravity is constant acceleration. The value is 9.8 meters per second squared, or we'll round it off to 10. Okay, let's go back to the diagram. Okay, so in the diagram here, right there, okay, let's go through systematically and ask what's the initial position, what's the final position, what's the initial velocity, and what's the final velocity. So in this diagram, you say, well, where should I start the motion? Where's t equals 0? I'm going to say this is where it initially starts. I know it starts at the top of the skyscraper. That's when I release it. But on my stopwatch, I get to start my stopwatch whenever I want. I'm going to start my stopwatch t equals 0 right when it passes the first window. So as soon as it passes the first window, I'm going to say, aha, that is my initial position. Now, you look at the ruler here and you go, can I measure that initial position? And the answer is no, you don't know it. You don't know the value. You don't know how far that is. In fact, if you look at the question, I ask you what's the distance between these two windows. That's exactly what you're trying to find. You're trying to find how high that window is above that one. In other words, how high window 1 is above window 2. So over here, you will say, I'll write just over here, I'm going to write x. And because it's the initial position, x naught, I'm going to say that's equal to unknown. Oh, sorry, that's a bad question mark, but you got the idea, okay? So basically, the initial position is just not known. I don't have a value on that ruler, okay, for that initial position. Even if I put markings there, I mean, where would it be? I don't know, okay? I can also ask what's the initial velocity. And I'm not going to switch back, but if you read the problem again, it says that the initial velocity was 10 meters per second. Okay, like that. At this point, we have to be very careful. Let me just look. Yeah, 10 meters per second. All right, we have to be very careful. Which way is positive in this diagram? Up is positive. Which way is the velocity? Which way is it falling? It's falling down. And so not only do you want a 10 there, but you actually want, sorry, I'm kind of squeezing it in there. You actually want a negative in there, okay? So the initial velocity, that is the velocity when it passes window number 1, we're going to say that's negative 10 meters per second. Negative because it's down. The 10 meters per second, I have that in the problem. Okay, I said that in the problem. But the negative is simply because it's going downwards. Okay, so ask if you don't understand what I did there. But I just simply said, you know what? I'm going to start my stopwatch at window number 1. Okay, so as soon as it passes window number 1, I start my stopwatch. That's t equals 0. That's initial. And what's that position? I don't know. Okay, what's that velocity? Well, I know it's 10 meters per second, and I know that it's down. Down is negative in this diagram. Okay, and so we've got initial position, initial velocity. Let's do final position. The final position is given the symbol x, and we know where that is because I chose the ruler to have a 0 right at that point. Okay, so I'm going to say that the final position is 0 like that. Okay, 0 meters. That's what you would read off of the ruler. All right, and then you say, well, what's the final velocity? That is, what's the velocity when you pass window 2? If you read in the problem, it says 15 meters per second. Okay, that's the English. But what direction? Well, up is positive, so it's falling down, so it's negative like that. Okay, let me look in the chat here. Could you have put x equals 0 at the first one? You could have. Yep, you could have. Okay. If you really want to see that, maybe I'll do it like after the live stream for you or something like that. But yes, you absolutely can put the 0 where you like. Okay. By the way, the numbers will be different when you work out the problem, but the answer would wind up being the same. Okay. On a test, usually I'll be pretty clear where I want the origin in case I've broken the problem down. I won't leave any ambiguities, but in general, yes, you could choose the x equals 0 wherever you want. Okay. So let's continue with our choice here like that. So we have an initial position, an initial velocity, a final position, a final velocity. So our one kinematic quantity is position, another one is velocity, the other one is acceleration. Okay. Now, like I said, we're gonna approximate that as 10 meters per, and the units are meters per second squared. But which way are you pulled when you fall? You don't get pulled up when you fall, you get pulled down when you fall. And so the acceleration due to gravity is negative 10 meters per second squared. Okay, because everything is going down in this problem. That's why you got a negative sign. Like when you pass the first window, you're falling down, negative. When you pass the second window, you're falling down, negative. When which way are you being pulled? You're being accelerated down, negative. Okay, and up is positive. Okay, so that's why all these negative signs are. One more thing, you might say, ask the question, at what time does it pass the second window? And you don't know. You just know that on your stopwatch, because you pressed t equals 0. When it passed the first window, you know that's 0, but you don't know the time when it passes the second window. And so that's another question mark like that. Okay? So that's step number 2 in solving these problems. So step number 1, you can see it there in black. Step number 1 is draw the picture, just as described by the English. Step number 2, I guess it may be 2 steps to step number 2. First part is put your ruler down and then identify your initial and final values. And for 1D, you could go in this. You can go in this order. You could say initial position, initial velocity, final position, final velocity, acceleration. And you don't do initial and final acceleration. Why? Because the acceleration is constant. All of this is under the assumption of constant acceleration. So the acceleration, it's not like the acceleration is more at the top and less at the bottom or anything like that. It isn't a velocity. So maybe I should just say a little bit about acceleration. Acceleration is how much you speed up over time. So you're speeding up at a constant rate. So you start off slow and then you're falling faster, okay? But the rate at which you speed up is a constant negative 10 meters per second squared. And maybe I can say just a little bit more about that meters per second squared. That means negative 10 meters per second squared means that every second you increase your speed by 10 meters per second. So if you start at 10 meters per second, a second later you'll be at 20 meters per second, and then 30 meters per second, then 40 meters per second. This tells you how much you speed up every second. Okay, so a little bit of an aside, but it's important to understand what we have. All right, so that's the end of drawing the diagram. Let me see if there's any questions in the chat. Okay, I know there's a 30-second delay. I don't see anything else. Let me switch back now to this. Okay, And so now we have all those numbers that we had on that diagram. Let me just transpose them to here. Okay, so let me transpose them to here. I think I can just cut and paste this. Yeah, right here. So there we go. Just cut and paste here like that. And actually we can just get rid of that one as well. Okay, so take a look. So all I did was I just transposed from the diagram to my whiteboard here the values that I wrote. So what did we have for our initial position? We don't know what that is. In fact, that's what we want to calculate. We want to calculate where the height of window number 1. And in our diagram, I won't switch back, but in our diagram, that was labeled as x0. That was the height. Okay, x0. X, that's the final position. That's the position after a time t. That was at window number 2, and that's where we put the 0 of our ruler. Okay, and again, you could have done it the other way around. You could have done it, so then in this case, x0, x naught would have been 0, and x would have been question mark. Perfectly legitimate choice. I don't know which you feel more natural. Okay, to me, they both seem the same, but if you find, like, because that question is, like, if you find it more natural, maybe to choose the initial position as x naught is 0, then you could solve for x, but I'll tell you, you would get a negative value for x, which makes sense because window number 2 is below window number 1. Okay, and then what was the initial velocity? That was the velocity when you pass window number 1, it was negative 10 meters per second. And then velocity when you pass the second window was negative 15 meters per second. And the acceleration was minus 10 meters per second squared as it was falling. Okay, all through the motion. Okay, so great. Now you have these numbers. And if you went through the diagram and you thought it through carefully, you're not going to make a mistake at this point. Okay, it's like literally the diagram is supposed to be like an experiment that you did. Okay, the verbal description doesn't describe the full experiment. It doesn't describe putting the ruler there. It doesn't describe what you would do with a stopwatch. Picture that in your head. Picture like actually putting a ruler there beside the skyscraper. Picture actually being by window number 1 and pressing a stopwatch when it gets there. That's t equals 0. Okay, and then I don't know how you'd be in two places at the same time, or maybe you have a partner, and then at window number 2, when it passes window number 2, you press the stopwatch and you see how much time elapsed. Okay, and we don't know that, so actually I should probably write that in there too. So the time elapsed in this motion is unknown. Okay, so all right. I mean, just look in the chat. Any questions? No more no questions. Okay, so at this point you're good to go in terms of plugging into the equation. Just look at the equations and say which ones do you want to use. So you take a look at equation number 1 and you go, oh, there's an x naught there. I could solve for that. I mean, it doesn't have to be, the thing you're solving for doesn't have to be on the left-hand side, okay? It could be any one of the variables in there. And you go, okay, well, x naught, this will solve for x naught, so I could use this one. But then you go, when you go to substitute in, if you try this later, you'll see that the t's are unknown. You don't know t. So you have x naught, which is unknown, and t, which is unknown, and that doesn't work. Okay, so equation number 1 will not give you the answer. Okay, you try equation number 2, again, we're solving for x naught. In question A, how far did it fall? Okay, how far apart are the two windows? We're solving for x naught, okay? And you look at equation number 2, and it doesn't even have an x naught in it. And so that's not going to work. It's pretty obvious that it's equation number 3. And once you've done a few of these problems, you realize that equation number 3 is the equation without time. If you don't know time in one of your problems, that's when you go to equation number 3. Okay, and so equation number 3 is the obvious one to use because time is unknown. In fact, these 3 equations are not independent of one another. If you take equation 2, solve for time, and put it into equation 1, you get equation 3. So equation 3 is really 1 and 2 with the time removed. Okay, so we're good so far. We've decided that we're going to use equation number 3. Let's do that. Let me just cut and paste equation number 3 like that. So what we'll say here, I'll just say in English, use equation number 3 like that. Okay, and then you just substitute in the numbers, and let me just do that very quickly by cutting and pasting like that. Okay, so what did I do there? Well, v, that was the final velocity. That was negative 15, so I put negative 15, but it's negative 15 squared. Okay, and then v naught, that was your initial velocity, so that was over here, that's negative 10, so it's negative 10. Whoops, I'm missing a squared there, like that. Okay, and I can't do superscript, subscript, so that little caret there, I think it's pretty obvious that caret means exponentiation. A lot of calculators do that. And so for v naught squared, you're going to have negative 10 squared plus 2 times a. A is that acceleration due to gravity, which we know was negative 10. Okay. And x is the final position. That's 0. That's where we put the 0, the ruler. And the initial position, that was unknown. That's the height of window number 1. Okay. And now, just expand out the numbers there. So this next line is just me doing some of the multiplication here, like that. So negative 15 squared is 225. Negative 10 squared is 100. 2 times negative 10 is going to be negative 20, but then it's going to be negative 20 times negative x naught. So there's two negatives there. There's a negative right there, and there's a negative there. And those two negatives will give you 20, okay, positive 20, all right? And then if you solve for x naught, you will get, ta-da, the answer, okay? And it turns out to be 6.25 meters, okay? You'll notice that when I substituted in the numbers there, I didn't put in the units because in this whole problem, I used MKS everywhere, okay? So that is meters for length and seconds for time. I didn't want to overly complicate this problem, so I didn't want to add an extra layer. But if I had given you those numbers in, say, kilometers per hour, then before you do this, you would have to convert to meters per second, okay? But there it is. There's the answer, okay? Make sure you actually answer the question, how far apart are the two windows? And you go, geez, does that really answer the question? And yes, it does, okay? And the reason it does is because, let's quickly go back to our window there. Sorry, our whiteboard here. And so window number 2 is at 0 meters. Window number 1 is, we know now, it's at 6.25 meters. So we can even write it in there. Let me do it in a different color. We know that this is 0 meters. We know that on the ruler, if you were to actually measure on the ruler, like there'd be little gradations on this ruler like that. Over here we have 6, we would actually read up here, we would read 6.25 meters. Okay, like that. All right, let me see. Any questions in the chat? No, not yet. All right, so that answers part A, and part A was, let me switch back. Sorry, guys. Switch back here. Okay, part A was how far apart are the two windows, and part B was how long does it take the rock to fall between the two windows? Okay, so how long does it take? Well, for this, you can, I guess you could recut and paste, your unknowns there like that. I don't know if you have to or not, but you could look at them again, and you can ask the question, what are you trying to solve for? And you're trying to solve for t, the time between the two, because we know it's at t equals 0, it's at window 1, and at that later time, t here like that, okay, t here like that, it's going to be at window 2. So we actually want to solve for t, okay, so question mark. So in this problem, there were two unknowns, okay? There was x naught was unknown and t was unknown. And then you can look back at these equations here, the three equations, and you could say, okay, well, which one do I want to use to solve for time? Well, you can't use number 3 because number 3 doesn't have time in it at all, okay? So it's either 1 or 2, and I'll be honest, if you have a choice between 1 or 2, 1 is a quadratic, and we're going to have to solve quadratics later, okay? But right now, well, actually, no, not later. I mean, even part of this section, we're going to solve quadratics. But when we get to 2D, we're going to be solving quadratics even more. Okay, so if you don't need to, try to use equation number 2 to solve for time because it avoids using a quadratic. And so for number 2 there, okay, I'm just going to take that and use equation 2 there like that. Whoops, I don't know, cut and paste failure. Okay, like that. And now just substitute in the numbers. Okay, so substituting in the numbers like that. Oops. All right, so what did I substitute in? For V, it's negative 15. For A, it's negative 10. For V naught, it's negative 10 as well. Okay. By the way, that's just a coincidence that they're both negative 10. Okay. And then solve for T, and it turns out that T is half a second. Okay. Turns out T is going to equal 0.5 seconds like that. Okay. And there, that answers part B, okay? And it's only half a second. Before I move on to the next one, let's see if we can understand why it's half a second. Let's go back to my picture, like that. And remember what that negative 10 meters per second squared means? It means that every second, the velocity is going to increase by negative 10. So if you start at negative 10, okay, you're at window 1 and you're at negative 10. How long until you're going to be at negative 20? Well, 1 second later. So you go from negative 10 to negative 20 in 1 second. Well, negative 15 is halfway between the two, and that's why you get half a second. Because every second you gain negative 10, so how long did it take you to gain just negative 5? Half of that, 1 second, or 0.5 seconds. Okay, so it kind of makes sense, right? Again, you'd expect you go from negative 10, you'd go to negative 20 in 1 second, but in half a second, you would go from negative 10 to half of 10, which is 5, and so from negative 10 to negative 15, and that's why it only takes half a second to go from one window, to fall from one window to the next. Okay, and that's it. Let me look in the chat here. Are there any questions with this one? So I said a minute ago, I made a mistake. I said that you don't need quadratic for this section. You do. Okay, I did a quadratic in the lecture, the pre-recorded lecture. I didn't want to repeat one of those same types of problems. I just wanted to do something different. But on the assignment that I'm going to give you for next week, I'm probably going to give you 2 different 1D kinematic problems, and at least one of them will have quadratics in it. Okay, remember, during these assignments, I know Canvas is their quizzes, but there's no time limit on them. So if you want, you could just leave the quiz alone, leave it, and then just ask me questions during my office hours in the evening. And by the way, I don't think I've mentioned this before, but if those office hours, they work for a lot of people, and a lot of people really like them. But I mean, if you're that one person that it's not useful, you can always shoot me an email. Don't worry, shoot me an email and say, can I ask you, you could ask the question in the email, or you could just say, do you want to jump in a Google Hangout? They take only a second to set up, and I'm more than happy to do that. So, don't feel that you can't get help during those assignments, okay? So I just thought I'd mention that at this point. All right, I don't see any questions about this particular problem in the chat. Okay, and so I'm going to move on. I just wanted to do something a little bit different than what I did for the lecture, so you could see more variety. And well, there it is. Okay, so let's see, we're about half an hour in. This next one is not going to take very long at all. Okay, so maybe we'll be done in about 15 minutes or so. Okay, so this is the second lecture I had you watch was on oscillators. Okay, and I wouldn't say there was a lot of theory there. There was more. I had to give you more talk about what was going on. Let me just remind you what an oscillator is. It's something which just vibrates back and forth like that. And since many things in the world vibrate back and forth like that, it's hard for me to say, to give you like one concrete example. Like practically anything that you nudge or you push will vibrate back and forth, okay? And it'll vibrate and then it'll eventually stop vibrating. What we did was we assumed no friction, so it would vibrate forever. But basically things are vibrating back and forth. And when things vibrate back and forth, they vibrate back and forth around a middle, and that's called equilibrium. That's where I place x equals 0 at the equilibrium. And they'll travel to one side and to the other side, so they'll be symmetrical around the middle, and they'll travel to one side a distance capital A and to the other side a distance capital A, and that distance is called the amplitude. Okay, and it takes a certain amount of time for it to make one complete cycle. That's called the period. That's given the symbol capital T, because little t is just how long, but capital T is how long for one cycle. Okay, we'll see capital T quite often in the course. And capital T is intuitively easy to understand, but unfortunately our equations have this omega in it, which looks like a W, and it's basically the angular frequency. And the angular frequency is just calculated from the period because it's 2 pi over capital T. All right. And then one last thing before we can jump into the problem. When it oscillates back and forth, it undergoes a maximum displacement that happens at the endpoints. Okay, obviously, because that's what amplitude means. It means the maximum displacement. Maximum velocity, well, if it stops at the endpoints, that's 0 velocity. So the maximum velocity happens in the middle, and the maximum acceleration happens at the endpoints. Okay, so maximum acceleration at the endpoints, maximum velocity in the middle, and of course maximum displacement at the endpoints by definition. Okay, so that's all you really need to know to solve this problem. Okay, so looking at the chat here, no extra questions. So let's just jump in. Let's just do it. Okay. So I say an oscillator, just generic oscillator. If you need to picture something, maybe picture like a pendulum, which is a string with a mass on the bottom, and the mass is going back and forth like that. Anything that just bounces back and forth. Okay. So this oscillator is found to have a maximum acceleration of 15 meters per second squared. Okay, and a period of 4 seconds. Okay, so once again, at the endpoints, that's where it stops and turns around. That's when it's being swung around the fastest. That's when its acceleration is the fastest. That's 15 meters per second squared. And the period, that is the time for it to go from one side to the other, is 4 seconds. So it's like 1001, 1002, 1003, 1004. And it makes one cycle, and then it does it again and again and again. Okay, so question number A. Okay, so this is a typical question I'll ask, because I do expect you to know at what point the maximas occur. At what point in the cycle does the maximum acceleration occur? And the answer is, I just said it, but write it down here, at the end points. Okay, at the end points. All right, that's where the oscillator stops and it starts to swing around the other way. Okay, at the end points. What is the angular frequency? So the formula for the angular frequency just depends on the period. Okay, now it's not a W, but I can't draw proper omega, so that W is my omega. Okay, omega. If you know your Greek alphabet, it's the last letter. It's the lowercase last letter of the Greek alphabet. Omega. Okay, and what's it equal to? So you need to know this formula. It's 2 times pi divided by capital T, where capital T is the period. Okay, well, that's easy enough because I gave you the period. I told you exactly what it is. It's 4 seconds. So you just get that omega is equal to 2. Pi is 3.14 approximately, divided by 4 seconds. And I'll put the units in here just to show you how the units work out. Notice that the seconds are in the denominator. So if you work this out on your calculator, you actually get, where's my number here? You actually get this number right there, like that. Okay, you get that it's equal to 1.57. And notice that the seconds are in the denominator, so it's actually per second. Okay, because it's a type of frequency, and a frequency is like how many times does something happen per second. Okay, and so that's why the seconds comes in the denominator. I mean, in a test, you'll either see per seconds, or you might see this other symbol called Hz, which is hertz. Okay, frequency measurements are often done in hertz. All right, and I mean, I'm happy to do 1/seconds, but the thing is that, like, in the future, even next semester, but in the future, you'll be even in your if you become PTs or whatever in clinical work that you wind up doing in the future, you might have instruments with frequencies on them, and you'll see the frequencies written in hertz. Okay, Hz. Or if you I mean, I don't know if anyone listens to car radio anymore, but if you're on FM, you'll see that it says like 88.8 megahertz. Okay, and that's again a measure of frequency. So you should know that 1/seconds is equal to hertz. Okay, and well, that answers the question. The angular frequency is 1.57 hertz. Okay, now what is the amplitude? And at this point you go, geez, how in the world can I get the amplitude? If you know the angular frequency and you know any one of the 3 maximas, you can calculate the other 2. So what are the 3 maxima? Maximum displacement, amplitude. That's what I'm asking for here. Maximum velocity and maximum acceleration. So maximum displacement, maximum velocity, maximum acceleration. I want to calculate the amplitude. It can be expressed in terms of the maximum acceleration. Okay, and so the formula there is, and our tests are open book, but it's good to know these so that you don't go, like, during the test, try to have as much memorized as possible, because this way you don't go searching for stuff during the test, because that'll eat up your time and then you won't get done. Okay, so the maximum acceleration, which I'll just write as A max like that. Okay, the maximum acceleration is actually equal to, let me just cut and paste this, is actually equal to omega squared times A. Okay, so A max is equal to omega squared times A. the maximum velocity is just omega a, which is our next question. But for the relationship between maximum acceleration and maximum displacement, which is the amplitude, it's maximum acceleration is equal to omega squared times a. Okay, and of course we're trying to solve for a, capital A, not for the acceleration, because I told you what the acceleration was. And so let's just rewrite this on the next line. So that arrow there just means I'm going to rearrange the formula. I'm going to divide both sides by omega squared, and I would get that equation there like that. Okay, so if I divide both sides of this one, I get by omega squared, I get that one. And now I can just substitute in the numbers. A is equal to, do I know A max? Well, yeah, because I told you. Let me scroll down a little bit more. I told you it's 15 meters per second squared. Okay, so over here, 15 meters per second squared, like that. And do we know omega squared? Well, we have omega, right? 1.57, like that. And square it, okay? And that gives me an amplitude of, that, okay? And at the end there, I put in the units, and I know what the units are. They are meters, because everything in this problem is MKS again. So if you go through the problem up here, take a look at the numbers. 15 meters per second squared, so the acceleration is MKS, and 4 seconds. So the seconds are acceleration, everything is in MKS. So you know that your answer will automatically come out in MKS. Okay, so it turns out that the amplitude of this motion is 6.09 meters. That's pretty big. 6 meters is like 6 times 3 is 18 feet. Okay, this is a huge oscillator. Okay, so there we go. There's the maximum acceleration. All right, let me take a quick look in the chat. No extra questions there. Okay, and now, what about the maximum velocity? So the equation for the maximum velocity is this. All right. So maximum acceleration, omega squared times a. Maximum velocity, just omega times a. Okay. And we don't have to rearrange this equation. It's already in the right form. So omega, do we know that? Yep. Omega is, I'll do it on the next line here. Omega is 1.57. And the amplitude, do we know that? Yep, we calculated in the previous problem, the previous part of the problem, and that's 6.09. And so omega 1.57 times 6.09, what's that going to equal? That will equal, and I should have the answer here like this. There it is. Okay, and again, I didn't use the units in there, but I know the units will work out to be meters per second. Okay, just to show you that they would work out to be meters per second, I'll just do this once. Okay, imagine that I put the units back in there. Let me put some space in there like that. Imagine I put the units in there. So what are the units of omega? They're 1 over second. Okay, so 1 over second. And what are the units of amplitude? Meters. Okay, so we have, let me space it out a bit there, like that. So we have a meter and per second. So a meter per second. Meter per second is a velocity. Okay, so in the opposite order, but obviously it doesn't matter whether you have the meters first or the per second first. It's going to be meters per second, which is a velocity. Okay, so works out. All right, and then the final question is, okay, at what point in the cycle does it occur? So it, meaning, let me just take that out there. At what point in the cycle does the maximum velocity occur? Just to be really clear that I'm talking about the maximum velocity. Where does that occur? In the middle. Okay, I'll draw a picture of this in just a second, but it occurs in the middle. So let's answer that. Okay, so max v occurs at equilibrium. And equilibrium is just, it means the middle of the motion. Or also in my notes, x equals 0, like that. Okay, there you go. All right, so that's it for the problems. I just want to draw a picture for you, but let me just see if there's any questions about what I've done so far. All right, I know there's a 30-second delay, but I'm not seeing anything. Let me just draw the picture of this oscillation, just so you know, so we're really clear about where this is occurring. Oh, I guess I should probably just create a new. How do I do new here? Oh, there we go. All right, there we go. Let me see how that looks. That looks okay. Yep. All right. And let me switch back to black. So Here there's an oscillator. This, what I'm drawing right now, is the path of the oscillator, okay? Like, I can't draw a movie for you, all right? And it's 1D, so this should be actually be like a flat line, but I can't, it's hard. If I draw a flat line, you won't see the motion. But basically, following my cursor here, it moves to the left, and then it stops, and then it moves to the right, and then it stops, and it moves to the left. The equilibrium, that's right in the middle here, right there, like that. Okay, let me do that in blue, right here. Here's x equals 0. All right, and where does maximum displacement occur? Right there. That's your amplitude. Amplitude means maximum displacement, like that, okay? Now, on the other side, you have maximum displacement. Actually, we could say x. X equals, okay, like that. You also have maximum displacement there, but because it's on the other side, we generally don't have to worry about this, but you could write negative a because it's on the left-hand side. If we take positive this way, okay, then this would be negative a and that would be positive a. But generally, because the motion is symmetrical about the equilibrium, we really don't worry about the negative and the positive in these. We just use the positive quantities. This is where maximum displacement occurs. Where does maximum velocity occur? Right in the middle there. That's where Vmax occurs. Okay. And where does maximum acceleration occur? Right there. That's where Amax occurs. Okay. Also on the other side, but it's negative on the other side. But like I said, I won't even worry about it. Just say Amax because, it's a mirror image. Okay, like that. So we have maximum acceleration here and the maximum acceleration there, like that. Okay, so the reason you need to know this is because I may ask it explicitly like I did in this question, or I might say the maximum velocity is, or no, I would say something like the velocity when it passes through equilibrium is whatever. And you need to know that when I'm saying when it passes through equilibrium, that is your Vmax, because when you go to plug into your equations, you're going to need Vmax, and you go, well, he didn't give me Vmax. He gave me the velocity when it passes through equilibrium. Well, that is the same. The velocity when you pass through equilibrium is your Vmax. Okay, so you need to know at which points in the cycle you get the maxima. All right, that's the end of the lecture. It looks like it just took us 47 minutes or something like that. So I'm just going to wait a few more seconds. And I'm going to switch back to my other screen here like that. And I'm just going to wait a few more seconds. At your end, when it gets to this point, it'll be just dead air. But that's because I have this lag going on. If I don't see any more questions, we'll just end the stream. Okay. Actually, let me even type it in the chat here. Does anyone have any more questions? Else we are done! Exclamation mark. Was that okay for everyone? Okay, great. Yep. Got one okay. As soon as I see someone chatted, I know that you guys have received the message at your end. Okay? So I'm just waiting a little more. If you guys just want to leave the chat at any point, or the live stream at any point, go right ahead. I'm just like waiting to make sure that everyone is okay. Okay, so this will be up online later, and you'll be able to watch it again. Okay, and don't forget, you can always catch me online, email me, or ask questions, and you will have an assignment on this material, including a quadratic next week. Okay. All right, stream is ending. Bye-bye.